In the last lesson, we saw how to use points to make copies of objects on a template. Actually, you should use copy to points instead of copy with stamp. So I replace this node. At this point, we can do the same thing we did before, and we can also delete this node. The result is the same either way, but this node is better and more useful for what we want to do. Before we move on, we need to figure out how to change the sizes of these spheres randomly, so that they are not all the same size. We also need to think about the properties of each point, which is a very important factor. If I go to the point replicate node and click on it, we get a group of points in space. The most important thing to know is that each point can have a set of properties assigned to it. We can open the geometry spreadsheet to see these properties. When we select a point, we can see the properties that have been given to that point. Right now, we see the position as a set of 3 numbers, x, y, and z. We can add any kind of attribute to these points. For each attribute, we can also give each point a different value. But how do we add a new attribute to these points? We can use the attribute create node to do this. So, let's pick the attribute create node and put it after the point replicate node. When we do this, we add a new attribute. The name for it is written in this field. And the number in the value field will be its value. This attribute is added to all points in the geometry spreadsheet. This attribute can have any value, and as we just saw, it can be a new attribute that we make ourselves. Or, we can add a native Houdini attribute that lets us change a certain property. For example, I can change the color of these points by writing CD in the name field, where CD stands for color. Because color is made up of 3 RGB values, we have to choose a vector as the type. At this point, if I change the second value, which is green, I give all the points the green color. If I type 1, 0, 0, the points are colored red. We can see better if we change the background of the viewport. Let's move the mouse over the viewport, press D, go to background, and set the display mode to dark. We can also hide the grid. Besides CD, there are other predefined attributes. For example, the size of each point is a native attribute in Houdini. The attribute name for the size is p-scale. It is a float value, not a vector one. Set it to a value of 1, so now every point in the point cloud has a p-scale value of 1. This is interesting, because each point's p-scale value also controls the size of the element that is copied to it. Select the Copy to Points node, and activate this checkbox. In this case, we can use the properties of each point to figure out the size and rotation of the copied geometric elements. We can see this if I turn on the display of points. If I set 0.1, the size of all the spheres will be 0.1. So let's repeat the step I just did, because it's important. I made an attribute create node that gave each point a new attribute. This attribute is called p-scale, which is the name of the native Houdini attribute that controls how big an object is. When we copy an object to one of these points, the p-scale value is also used to determine the size of the copied object. This is why we can use this native attribute to set the size of all of these objects. I can also get rid of the transform node and connect the pack node directly to it. Now, we can change the size of all the objects by changing this value. But we don't want to set a single size, as the result would be the same as with the transform node. We want this value to be random, so that each point's value for this attribute is different. So, we need to give each point a random value for this attribute. This can be done with a different node called attribute randomize. This node is similar to the attribute create1 in that it makes a new attribute, but this time it makes random values between a minimum and a maximum value. Let's see how it works. I'm removing this node from the flow. Then, I'm going to connect the attribute create node. First, it changes the color of the spheres, because now CD is set as the attribute to create. The attribute of color was automatically added to each point. Because the color is made up of 3 parts, we need 3 values. This node makes a random number between the minimum and maximum values we give here. This is done for each of the 3 values that make up the 3 RGB components. I can also change the size attribute in the same way. So I write p-scale instead of CD. Because this value is float, I don't need 3 dimensions. I need only 1. From what you can see, the result is a random number between 0 and 1. These values can be changed. I set the lowest value to be 0.1 and the highest value to be 0.3. So, each sphere has a size that is somewhere between the minimum and maximum value. We can go down even further, like this. And the end result is a bunch of spheres that are all different sizes. Let's make sure the simulation works before we change the shape of these things to make them look more like rocks. To do this, we need to use the group of spheres we made instead of the single sphere. This transform node can be removed. So let's use the spheres we just made. Let's turn on the display of the node in the dope network. If we start the simulation, nothing happens, because all the spheres are exactly on the floor. So we need to move the origin of the points upward. I choose the point replicate node, and then move the point origin in the shape panel. We can now start over with the simulation. We basically have a group of objects that moves in response to the force of gravity. So, when they fall, it's like a bunch of marbles hitting the floor. And this is how it turns out. This shows that our simulation works, even if we use more elements as the source. Now I'm going to change the sphere. We can use a very useful node to make the sphere a little more uneven. This is the mountain node, which makes a surface look bumpy. I choose the node and move it so that it comes after the sphere node. Turn on the visual representation of this node so we can pay attention to what is going on at this point. The surface of the sphere changes as the noise is added. At this point, we can change how the noise is made. For example, we can change the amplitude, which makes the points move farther or closer together. In the same way, we can change the type of noise that is made by picking one of these. Because each type of noise is a different algorithm, the results are also different. We can also make the size of element parameter bigger. Or you can move the offset. We'll keep going until we get the shape we want. At the moment, the quality isn't very good, because there aren't many faces on the sphere. So the resolution of the end result is also low. Because of this, we need to add more faces to the sphere. By doubling the number of rows and columns, for example, the end result has a more rounded shape. Through the smooth node, we can smooth things out even more. When we're done, the edges are smoother and the shape is more natural. Now, we can turn on the copy to points node again. We get a set of elements that are spread out in a way that is less even than before. But there's another problem. We have a more natural shape, and the sizes of our objects is now different. But we need to add another element, which is a difference in how these objects are rotated. Right now, they are all oriented the same way. But how do we change the way all of these points are facing? You might think that, just like the p-scale parameter, there is a rotation attribute for each point, which controls how all of these objects rotate. In fact, there is another way to be able to do this. Select the Copy to Points node. There is a property here, in which normals determine how objects are oriented. So, you can change the way each object is facing, by changing the normals for each point. But, what are normals? The normals are vectors that are perpendicular to the surface they belong to. We can make a new object, like a sphere, to get a better idea of what they look like. With this button, we can show the normals related to the different faces. As you can see, the normals are just this vector that runs perpendicular to each face. So, they face in different directions. But there are also normals for each point, in addition to the normals for the faces. So we can also turn on the normals display relative to points. But right now, we can see that for each point, it looks like there are 4 lines. This is because normals are automatically given to vertices. We can add a new node called normal to add the normals to points. This gives us lines that start from each point. But why did we consider this? Because if we look at the point cloud again, we can give each of these points a normal. The final orientation of the objects will be based on how these normals are oriented. So the plan is to do it the same way we did it before. We made a new attribute called p-scale, and then we randomized it. I can make the normal attribute in the same way. And give it some random values, between a minimum and a maximum. So I add a new attribute randomize node. As usual, CD is the default value for the attribute that is made. We need to make the normal attribute, though. The name of the attribute is n, that has to be written capital letter. Since the normals attribute is a vector, there are indeed 3 dimensions. If we turn this node on, we can see that normals have been added to the points. And each of these normal points in a different direction, because we have a random value between the minimum value and the maximum value. In reality, the minimum value should be -1, not 0, so that the line can go in any direction in 3D space. Here, we can see vectors that start at each point and go in every direction in space. This direction will also determine how the rocks are oriented in the space. So, we have spheres that have different sizes and are arranged in different ways. Now we can activate the dope network and start the simulation over again. This is what happens. Now that we have all the parameters defined, we can, of course, change some settings, like the amount of rocks or the distance from the ground. I also want to make a bigger area where these points are spread out. So, I go back to the Point Replicate node, open the Shape panel, and make this area bigger. I can also change where these objects start, or add more points. For instance, this. At this point, it's important to remember one thing. When we look at each of the rock we've made, we can see that the shape is basically the same. There is some variation between them as the rotation and size. This is because, as we've already said, we used a single packed object that was copied several times. This saves a lot of memory, but now we have a lot of objects that are the same. We can't keep going this way if we want completely different objects. In this case, we should use other methods, which we may look at later. If you remember, we created this plane in a previous lection by adding it inside the dope network. In fact, if we go inside it, we have this ground plane, which automatically adds this infinite plane. As you can see from the arrows, the plane goes on forever in every direction. This element was automatically configured to be an impact surface for the rocks. But we want to create an uneven surface, not a perfectly smooth plane. First, we have to make a new object with the shape we want. In my case, I want to create an irregular surface. I therefore add a grid with the grid node. Now we need to modify this node to have an irregular shape. And we have already seen how to add noise to a surface. We can do this with the mountain node. But first, I want to increase the resolution of the grid by increasing the number of faces. At this point, I'm going to add another mountain node and change the parameters to distort the grid. We can finally add the smooth node as well. Okay, at this point we need to use this object as an impact element for the rocks. We then need to act similarly to what we did for the rocks. That is, this object needs to be imported into the dope network. I'll also split this panel in half, so that two groups of nodes can be seen at the same time. The top panel remains anchored with the view of the geometry nodes. In the part below, we have the dope network nodes. We can then disconnect the ground plane. Now we need to import the new ground we made. But we don't have to use the RBD packed object, which is what we used for the rocks. Among the objects, we see that there is another type of object, which is the static object. As you can see from the icon here on the left, it represents a kind of wall. That is, something that acts as a strike plane. So an object that, as the name implies, is not subject to the force of gravity or other forces, but simply serves as an impact element for other objects in the simulation. I have to set which object to refer to. In our case, the grid we created. In this case, I can't set the input where the object will come from. Instead, I have to directly refer to the object I want to import. It is a good practice to add a null node to the end of a node chain of an object. By convention, we prefix this with out, written with all capital letters. For example, out ground. This because, when I look for the object to be imported, it is at the top of the list of nodes, because it is written in all capital letters. So, select this out ground and connect it with the merge node. We see the grid within the simulation. This plane, being a static object, is not subject to the forces of gravity, but only acts as an obstacle for the other elements inside the simulation. Let's start the simulation and see what happens. The objects fall this time, but they hit the floor in a strange way. The objects look like they are floating above the floor. In order to understand why, we need to introduce another important concept. That is, the geometry that is actually used to compute the simulation. In fact, the geometry of the object and the geometry that is used to calculate the simulation are two different elements. Therefore, we need to think about what shape, in relation to both rocks and ground, is actually used to calculate the collisions. Let's look at this single rock to better understand the difference between the real surface of an object and the surface that is used for simulation. Then we'll look at how both surfaces are represented. This is the surface we created, which represents the object. But when we add this object to the simulation, we need to calculate its interaction with other objects. In order to do this, a simplified version of this surface is made, so that the simulation calculation is easier. For example, a surface that looks like this one. So, basically, an envelope is made on the outside of the surface. It doesn't exactly match the shape of the surface, but it's a simplified version of it. This surface is always convex, so it does not follow the shape of holes or depressions. It's kind of like a shell. We can see this surface by analyzing the properties inside the solver. Let's go back to the dope network and choose one of the objects we added, like this RBD packed object. Among the properties of the bullet data, we have this checkbox, Show Guides Geometry. Let's get a closer look at the rocks. This is what we saw when we looked at this Guides Geometry. So the geometry that is created to simplify the shape of the object. If we turn off the display of the original geometry, we can see the surface that Houdini sees to simulate the collision. It has a blue color. If we also turn on the original geometry, we can see that the guide geometry is roughly the same shape as the object, but it always stays convex. For example, in this area we have a concave shape, while the guide geometry always remains convex. This makes it a lot easier to figure out the geometry, which makes the simulation calculation go very quickly. We can change how this geometry is made by changing this property, which is called geometry representation. This is the geometry that the simulation actually uses. The convex hull setting is used by default. As the word convex suggests, it is a convex surface that follows the outer perimeter of the actual surface. But there are other ways to represent the geometry that are even simpler, and they are listed here. We could, for example, represent it through a simple box, or capsules, spheres, and so on. Clearly, the simpler the geometry, the faster the calculation, but the less accurate the simulation calculation will be. Obviously, if we use a sphere to simulate something that isn't a sphere, it will behave very differently when it hits the ground. But in some situations, it might be helpful to use these simple shapes. The concave that we see here is the most accurate way to show what the object looks like. As you can see, it makes a simulated surface that exactly matches the shape of the original geometry. But this kind of guide geometry is hard to calculate, which can slow down the simulation. And sometimes the results are even worse than when we use the convex hull. So, unless there are special needs, the convex hull is always the best choice. Let's see what happens with our collision plane. So let's try to figure out why the simulation acted in this strange way. Select the static object, and in the bullet data activate Show Guide Geometry. Here, it's easy to see that, because of what we said, the impact surface has no holes. So it's clear that the surface is very different from the original one. These are the curves of the original surface, but the convex hull gives us a shape that is always convex. Since it can't become concave, the top of it is flat. Because of this, the rocks get stuck up here at the top. So, for an uneven surface like this one, we need to change the representation type from convex hull to concave. This time, the guide geometry is a perfect match for the shape of the surface. If we start the simulation, the stones also roll through the valleys of this surface, which is what we expected to happen. We now have a realistic simulation that is exactly what we expect for a simulation of this type. In the next lesson, we will consider the last aspects to complete this simulation, which are some physical properties with which we can control the behavior of the simulation. In order to control our simulation even better, we can access a whole range of physical properties of the objects themselves, which are the same properties we find in nature, such as mass, friction, tendency to bounce, and so on. We can set these properties for both moving and still objects, like the ground in this case. So, if we start from rocks and move into the Physics tab, we have several properties, the first of which is the so-called compute mass. So, if an object has a certain density, the mass is automatically calculated based on the volume of the object. If we disable this parameter, we can define a mass, which will then be the same for all objects. The mass is important because the type of impact with other objects depends on it. The other parameters that are generally used are bounce and friction. Bounce refers to the elasticity of an object, which is why it tends to bounce. For instance, if we set this value to 0, these objects will be less likely to bounce. As you can see, if we change the value to 1, the way the objects bounce changes. The static object has these same parameters. So, I can change the property bounce and friction, and the final effect is even stronger, because I increased the properties in both the ground and the colliding objects. Let's go back to the 0.5 value for both objects. Friction is the other important property, and everyone knows what that means. It is the tendency of objects to be restrained in their motion on a surface. If I take away all friction from the rocks and the floor, it's the same as if they were on ice. The objects keep moving without stopping. We are not interested in the other parameters right now. We will consider them later. Another important attribute is the collision padding. It is a property that both static objects and active objects have. It represents the distance between the actual surface of the object and the collision surface. So the greater this padding, the greater the distance between the real surface and the surface that is used to calculate the simulation. It may be useful to increase this parameter when two objects do not collide properly. For instance, if one object goes through another. On the other hand, we need to lower this value if there is too much space between two colliding objects. In the previous lessons, we learned how to run a simulation in which gravity is the only force. But what if we want to use other forces in the simulation? Take a rock and throw it in a certain direction, for example. We can do this in a few different ways, which we'll talk about here. Let's start by making a new file and adding a simple sphere to it. You can do this yourself, as we saw in the last lections. As a practice, I'm going to move quickly through this. Well, we've seen how to do the simple simulation with only gravity. And this is the result. So, as we've seen before, the sphere just falls down. But, as I already said, what I'm going to do is to give it an initial speed, so that we have a force in addition to gravity. The easiest way to do this is using a property of the RBD object itself. In the initial state panel, we can choose the object's initial state. We can also set a value for the initial speed along the x, y, and z axes. I write 8, for example. This means that there is an initial speed of 8 along the x-axis. If I start the simulation, the sphere moves in that direction and then stays subject to the force of gravity. If we move the sphere a little higher, we can see this even better. I can also increase the initial velocity, bringing it to the value of 10, for example. When we look at the simulation closely, we can see that the impact happens in a strange way. It's like the ball bounces and then speeds up all of a sudden. We need to look at the surface used for the simulation to get a good idea of how the impact works. So, if I turn on Show Guide Geometry and turn off Display Geometry, we see the surface that is used for the simulation. Here is a sphere with many different sides. These faces could determine the abnormal behavior. One thing we can do is increase the sphere's resolution. So I go back to the Dynamics panel, select the sphere, and increase the subdivision of rows and columns. The resolution of the surface used for the simulation is also higher. Let's see what happens. Even so, the problem with the simulation is still the same. Let's reset the default values. We can also change the surface of the simulation. As you can see, there are several options for the geometry representation, including just a sphere. In this way, a shape that is perfectly round is made. Indeed, if we start the simulation, the behavior is definitely better than before. But there is still a small problem. After the sphere hits, it almost seems to speed up all of a sudden. We need to think about a different idea to solve this problem. Select the dope network. In the simulation pane, there are a number of settings, one of which is called substeps. This parameter is very important because it controls how many calculations are done for each frame. In this case, a single calculation for each frame. Let's try to figure out what this means. If I move forward one frame at a time on the timeline, the sphere moves exactly this far between two frames. If the number of substeps is 1, it means that a single calculation is performed in this path. So, any forces or interactions between this position and this one are only calculated once. If I increase this number, it means that more calculations are done between these frames. This makes the simulation more accurate. For instance, I might change the value to 4. Move to the beginning of the simulation and start it over. The impact happens more smoothly. This is because the number of calculations for each frame has been increased. Of course, the greater the number of calculations, the longer the calculation time of the whole simulation. In any case, it can be useful to increase this value when we are dealing with complex simulations, in which we notice anomalous behaviors in the interaction between the objects.